Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We are discussing the topic digital electronics. Especially, we are in the section simplification of Boolean expressions. In the previous lecture, we have seen how Boolean expressions could be simplified with the help of NAND and NOR gates. We have seen two forms of writing the Boolean expressions, the product of sums and the sum of products. For implementing the sum of products, we used NAND gates, and for implementing the product of sums, we used NOR gates. These details we have learnt in the previous lecture, but we have used only two variable systems. What is the meaning of two variables? We have restricted ourselves with only the inputs A and V. We have not gone for the variable with higher values, higher inputs like A, B, C, D, etc. In this lecture, we are going to see the necessity for many input gates, and also we are going to learn about the one more technique for the simplification of Boolean expression. Before we move on to the lecture of today's session, let us have a look at today's session outline. In this session, we are going to see the importance of many input gates and also the simplification of Boolean expressions using Karnaugh map. When we consider the Boolean expressions, we will be having many inputs. For understanding the basic concepts, we restricted ourselves with only two inputs, namely A and B, or sometimes in some textbooks it is represented as X and Y. But whatever it is, we restricted ourselves with only two inputs for getting the core understanding of the concepts. But now it is time for us to look at the concepts related to many inputs or many input gates. When we have a look at the general Boolean expression, based on the number of inputs, the expression will also have that many variables. So, while handling such expressions, we may have to sometimes directly implement the expression in the form of the circuit with gates. So, for that we need many input gates. So, let us see the necessity for the many input gates, and we will be having a look at the typical IC chips containing many input gates also in this lecture. Now, the necessity for many input gates. For understanding the basic gate operations, we have taken gates with only two inputs. In general, we have logical expression with more than two variables. Hence, getting the idea of many input gates is necessary at this point. This is given as an example here. Here the two variable expression involving A and B only is shown here. It is in the form of product of sums. And here is the example given for 3 input expression. We have A, B and C and many variable expressions A, B, C, D, E if possible, D, E, F, etc. So, sometimes we will be coming across the expressions with many such inputs. So, will it be possible for us to design a gate which could accommodate many such inputs? To some extent, in the chip level itself, the IC chips, they have incorporated many input gates. Though there are a lot of restrictions, if we increase the number of inputs, the number of gates that could be accommodated in a chip will also get reduced. But nevertheless, if the case warrants such a many input gate, we may have to use them. So, there are some ICs available with many input gates. And also the truth table that we write for many input gates will also become lengthy and little exhaustive. So, we should be equipped to generate all possible combination of inputs, but there is a particular order in which when we write the combination of many inputs, we will be able to write them all in a sequential manner. So, all this we will see now one by one. So, before we go into the typical expression, let us have a look at the IC chip which accommodates a 3 input NOR gate. So, this IC is IC 7427 which accommodates the 3 input NOR gate. If you could recall to our mind, in normal the 14 pin IC 74 series, if the inputs are 2, we could have 4 gates that we have seen in one of the earlier lectures. But here, because the input is 3 inputs, we are restricted to only 3 gates. So, we have to sacrifice the number of gates if we want to accommodate many such inputs, and this is a 4 input NAND gate. IC 7420 is the 4 input NAND gate IC, and here because it is having 4 inputs, we are again sacrificing the number of gates. Only 2 gates are integrated in this chip. And another thing is, if we could notice, the pins 3 and 11 are no more in use, because it is only 2 inputs are available which could not be used for any purpose. So, such many input ICs are also available. When we directly want to implement the logical expression with 3 inputs, 4 inputs, etc., to some extent we could accommodate them using the many input ICs. So, this gives us such an idea. And as I said earlier, the combinations, what are the number of combinations or what are the combinations themselves, we need to concentrate on that also. We should not miss any of the combination when the input becomes many in number. So, let us have a look at the combinational possibilities for many input gates. The input combinations also will become many as the input variables become many. In the case of 2 input variables, the input combinations are just 4. In the case of 3 input variables, the input combinations are 8. In the case of 4 input variables, the input combinations are 16. Each time you increase the variable by 1, the number doubles, the combination number doubles. That you could notice. There is a formula governing the input combinations. The number of input combinations is given by 2 to the power n. Here n is the number of variables in the expression. So, in a nutshell, if you want to say, if you increase the input variable by 1, then the combination will double in number. For 2 input, only 4 combinations are possible. For 3 inputs, the combination becomes 8, and for 4 input the combination becomes 16, and so on. Let us have a look at the combinational possibilities for the inputs which right now I have mentioned. See, this is the input combinations. For 2 input, for A and B it is 0 0 0 1 1 0 1 1. So, these are the 4 possible combinations. For 3 input, the 8 combinational inputs are possible, and for 4 inputs there are 16 inputs possible. The A, B, C, D, each combination will differ from the other at least in any one of the inputs. See, if you take the first 2 combinations, the difference is only found in D, and between the second combination and third combination the difference is found in 2 places. In C and D it is varying. So, like that, it is a very simple technique. By permutation and combination we will be able to generate all the inputs for the given number of inputs. All the combinations can be generated. And why do we have to consider the many input gates? Because as the operations are meant for taking care of difficult circumstances, maybe many inputs are required. So, we need to use the many input gates in several circuit simplifications, and also in the binary system to represent each character we would be using only the digital inputs as per the ASCII system, which all I have covered in the very early lectures of the digital electronics. We may have to 256 such characters are to be represented using zeros and ones. So, many such combinations are required. So, for all that, this many input gates will be very much useful, but there are some techniques which could also be used to expand the number of inputs with a standard number of input gates. We need not every time go for a particular high input gates, but we can expand. There are some techniques. When we learn digital electronics as a core subject, we will learn all of them. But right now we just touch upon the important aspects of digital electronics. Now, I would like to introduce a new technique which could also be useful for the simplification of Boolean expressions. What are the techniques we have been using so far? We used the De Morgan's theorems, and also we learned a lot of identities, the standard results of the Boolean algebra we have used. But every time we may not be able to manually sit right and simplify the given expression. We may have to use some tools, some techniques which could come in handy for handling such simplifications. So, today in this lecture I would like to introduce a very common or very interesting technique called the K-map technique. The K-map is the short form for Karnaugh map. What is Karnaugh map and how it is used, we are going to learn now, which is very much useful for simplification of Boolean expression. So, let us see what is Karnaugh map. We will continue to see that after a short break. Welcome back. We are discussing the simplification technique using Karnaugh map. Let us see what is a Karnaugh map. Let us have a look at the slide and learn what is a Karnaugh map. The Karnaugh map, also known as the K-map, is a method to simplify expressions of Boolean algebra. The Karnaugh map reduces the need for extensive calculations by taking advantage of humans pattern recognition ability. It also permits the rapid identification and elimination. So, in a nutshell, Karnaugh map makes use of the human recognition ability, the pattern recognition. We need to represent the zeros and ones according to the expression in the Karnaugh map and identify how they are placed, how they appear in the Karnaugh map. So, let us see what is a typical Karnaugh map for a 2 variable, 3 variable and 4 variable expressions. We need to construct the Karnaugh map and place ones and zeros in the squares according to the truth table. Group the isolated ones which are not adjacent to any other ones, which is called a single loop, and if we could group any pairs, that means 2 characters which contains a one adjacent to only one other one, which are called double loops. Group any quad means here 4, that contains one or more ones that have not already been grouped, making sure to use the minimum number of groups. Group any octet, here octet is 8 such characters clubbed together, even if it contains one or more ones that have already been grouped. So, in essence, we need to represent the zeros and ones in the Karnaugh map according to the Boolean expression, and then have a look at the Karnaugh map so that we could find out the ones in terms of pairs, quads, octets, etc. The 2, 4, 8, such combinations we should recognize and club them together. So, when it is theoretically mentioned like this, we may not be able to fully understand what is the Karnaugh map and how it is represented, the zeros and ones, quads, octets and all that. We are going to see how a Karnaugh map would appear. It is nothing but a matrix representation. It will have rows and columns. It is just a table. Though it's called as map, it is just a table which could accommodate the zeros and ones according to the expression. So, let us see what is a Karnaugh map and how it looks like. And after we group them, we need to sum them up and write the final expression. There are techniques which could help us to write the output as sum of product or product of sums. We are going to see them all. See, this is a 3 variable expression. It has A, B and C. See, here when we say the 3 input, the complements are also taken into account. When we say A, B, C, the A complement, B complement, C complement are also the terms considered in as the input. So, it is simply called as 3 input expression, though their complements are there. So, this is one such expression. For this combination, the output is 1. That is what it means. We get an output 1 for this combination of the input. So, what we have to do, this is a expression in the form of sum of products. The products, there are 4 products here, A bar B C, A B bar C, A B C bar and A B C. These 4 products are summed up. So, it is called sum of products, and we need to form a K map in this manner, because it has 3 inputs. We take A in the x side in the vertical line and the B and C in the horizontal side, and we have this 8 boxes generated, and A0, B0, C0 is this box, A0, B0 and C1 is this box. It goes like that. So, it's well understood. If you could have a look at the box, there are 8 boxes possible. As I said, if it is a 3 variable system, there are 8 combinations possible for the A, B, C, right? 3 input. So, it is 2 to the power 3. There are 8 combinations possible. Each box represents one such combination, and if it is in the sum of products, for each product we need to identify and put 1. See, the output is maximum. It is called all the ones with maximum grouping. So, we represent where is the A bar B C box. So, this is the A bar B C box. So, put 1 and similarly A B bar C box, where is it? A B bar C. I think A B bar, A is this and B bar C is this box. It's like that 1, 2, 3, 4. There are 4 products. So, for them the ones are written and we have to fill the remaining with zeros. And after writing them, what we need to do? We need to identify the ones and try to club them together. We have to go in terms of even numbers only. See, here in the vertical we could club these two ones together. In the horizontal, these two ones together, and again one more possibility is there. But as far as this one is concerned, it is participating, it is shared by the two pairs taken this way and here this way. So, we can overlap when we consider the ones together, when we form the pairs, octets or quads, we can consider a particular box for many such pattern recognition combinations. So, here also one example, this one is shared by these two pairs. So, that kind of thing is possible. But after that we have to write a simple expression. So, look at this, there are 4 such pairs, each pair could be written as a term here. When we consider this vertical pair, it is having the BC, for B and C only it is 1 1. So, that BC is written here. When we consider this pair, it is, we have C and A, A is also A and C, for C it is 1. So, AC pair is written, and for this one again A and B, B has 1 common. So, this is the simplified expression. When we compare the input and the final output, the terms are very much reduced. See, in the input we have 4 such products, each product having 3 terms, but in the simplified expression we have only 3 products, 1 product is reduced, and that too each term has got only 2 variables. Here it is AC, here it is BC, here it is AB. So, the expression is very much reduced. We have not used any other technique, we have not used the identities or De Morgan's, whatever it is, but we use the K-map technique. Actually, the K-map technique is an improved version of De Morgan's. De Morgan's is always true, but that is a basic rule. But this Karnaugh map helps us to implement the De Morgan's rule in a very effective way. When we use only De Morgan's, the number of steps we do, no, it will be very many. But here in 1 second or within a flash, we are able to write the expression without much difficulty. Only thing is, we need to identify and recognize the pairs, quads and octets, etc. So, this has given one typical idea for us how the expression is reduced. We have lots of such examples. I will quickly run through few of them and we will have a greater understanding. See, this is a pair identification. When we have a look at this, see, it is written, there are 2 terms written here. So, 2 terms are there in the original expression for x, and after identifying this pair, we have only 1 term, it is BC. By the De Morgan's or by the identities also, we will be able to arrive at the answer. And here also the same way, the horizontal way the pair is recognized, and this is again a interesting combination. If the ones are at the extremes, we can also club them together. It is like, see, when we have a flat table, when we are folding it, the extreme terms come together. So, that is how we are able to recognize this pair. So, this pair is also possible. Similarly, horizontally also it is possible. This is a 4 variable input. So, in the original expression there are 4 such terms, 1, 2, 3, 4, but after it is clubbed, these 2 form 1 pair, these 2 form 1 pair. So, only 2 terms. So, without much difficulty, quickly we are able to reduce the number of terms using K-map technique. And in K-map technique, when we recognize the ones, the terms ones, we will be able to comfortably write the expression as the sum of products, and we can quickly migrate to the product of sums also. So, that advantage is also there in the K-map. I will explain how that migration is possible towards the end of this lecture, but before that we will see few more such pattern recognition. Especially we should be trained in recognizing the pairs, quads and octets. Only that ability we need to develop, otherwise it is very simple technique. Now, for a quad, see, we can have a quad in the vertical line, 4 terms, horizontal, even the 4 could be considered as a square pattern, and here also, as I said, the rolled table, that will also have the quad formation. The quad could be taken in the 4 extremes also. It is like you fold them horizontally, also vertically. In that case also these 4 terms will come together. So, in any possible manner we should be able to recognize a quad in this way. And now we will have a look at how an octet is recognized. See, in the case of octet recognition also, 8 terms, they could be in 2 separate rows, horizontally, vertically, and again in the rolled formation. When the table is rolled horizontally, the 8 ones will come together. Here it is rolled vertically, the 8 ones will come together. One thing we can wonder in this K-map, see, there are 8 ones written, 8 1 values. Each one term is represented by 4 combinational input. Like that, there are 8 inputs, 8 terms in the original expression. But once it is identified as an octet, see, one single term, only the B is the common thing for the entire octet, so that is only written. So, the 8 terms get reduced to a single character B. Do you understand? 8 products, each product having 4 inputs, a very long expression, lengthy expression is getting reduced to a single variable input B here. So, this is the power of K-map. The only thing is we need to train ourselves in recognizing the quads, octets and pairs, etc. Now, how do we write the final expression? So, as I said, it is to be considered for writing the final expression for maximum. And we have one more interesting case, it is called don't care condition. In certain cases, some terms may never occur or it may not matter what happens if they do. In such cases, we fill in the Karnaugh map with the term x. Here x means don't care. When minimizing the x, x is like a joker in the card game. It could be either considered as a 0 or it could be considered as 1, whatever helps the best in minimization. See, the don't cares in expressions appear like this, and that could be considered as zeros or ones as we like. So, the don't care and all that comes in the K-map. So, if we are interested to know more about the K-map simplification, I have just given a gist of the K-map, the introductory stage. It could be developed further, which will help us a lot in the simplification technique. There are a lot of interesting facts hidden in the concept called K-map. Now, how do we write the terms as sum of products and product of sums? As I said, if we recognize the ones, we get the sum of products. If we recognize the zeros, then we get the product of sums also. It is because of this explanation which I have given. If we consider the zeros, complement of complement will get nullified. See, this term is getting reduced in the form of a product of sums also. So, this is the advantage of using a K-map. Now, it is time for us to look at today's summary. In this session, we have seen the importance of many input gates, simplification of Boolean expressions using K-map. Let us test our understanding by answering these questions. What is Karnaugh map and what for it is used? Simplify the Boolean expression using Karnaugh map. It is a 4 input expression. What is don't care condition and how it is useful in Karnaugh map simplification? So, the concepts of Boolean expression simplification using Karnaugh map we have seen today. So, see you in the next lecture with the concepts of integration and differentiation using discrete electronic components. Thank you for watching. All the best.